In physics, physical quantities are the measurable attributes or properties of physical systems. These quantities can be categorized into two types: fundamental quantities and derived quantities. Fundamental quantities, also known as base quantities, are the basic building blocks from which all other physical quantities are derived. They are independent of each other. In the International System of Units, there are 7 fundamental quantities: 1. Length, measured in meters; 2. Mass, measured in kilograms; 3. Time, measured in seconds; 4. Electric current, measured in amperes; 5. Thermodynamic temperature, measured in Kelvin; 6. Amount of substance, measured in moles; 7. Luminous intensity, measured in candelas. Derived quantities are those that are derived from the fundamental quantities through multiplication, division, or other mathematical operations. Examples include velocity, which is length divided by time, measured in meters per second; acceleration, which is velocity divided by time, measured in meters per second squared; force, which is mass times acceleration, measured in kilogram meter per second squared or Newton; work, which is force times distance, measured in kilogram meter squared per second squared or joule; power, which is work divided by time, measured in kilogram meter squared per second cubed or watt. Units of measurement are standards for expressing and comparing the magnitude of physical quantities. Each physical quantity has a unit assigned to it, which is used to express its measurement. The International System of Units, or SI, is the most widely used system for measuring physical quantities. It provides a consistent framework for measurement worldwide. The 7 base units in SI are: first, we have the meter, abbreviated as M, which is used for length. Next, there's the kilogram, or kg, for measuring mass. Then the second S, which is the unit for time. Following that, we have the ampere, A, for electric current. For thermodynamic temperature, we use the Kelvin, abbreviated as K the mole. Mole is used for the amount of substance. And finally, the candela, CD, which measures luminous intensity. Dimensional analysis. Dimensional analysis involves using the dimensions of physical quantities to analyze the relationships between different physical quantities. The dimensions of a physical quantity are represented in terms of the fundamental quantities. For example, velocity has the dimension, LT circumflex, -1, and force has the dimension, MLT circumflex, -2. Importance of units and measurements. Firstly, accuracy and precision. Using standardized units ensures that measurements are accurate and precise, which is crucial for scientific experiments and engineering applications. Secondly, consistency. Consistent units allow scientists and engineers to communicate their findings clearly and without ambiguity. And finally, conversion and calculations units enable the conversion of measurements from one system to another, for instance, from SI to the imperial system, and allow for consistent calculations in scientific and technical work. Examples of measurement. Measuring length. Using a ruler or a measuring tape, lengths can be measured in meters, centimeters, or millimeters. Measuring mass. Using a balance, masses can be measured in kilograms or grams. Measuring time. Using a stopwatch, time intervals can be measured in seconds, minutes, or hours. Measuring electric current. Using an ammeter, electric current can be measured in amperes. Measuring temperature. Using a thermometer, temperature can be measured in degrees Celsius or Kelvin. Measuring luminous intensity. Using a photometer, luminous intensity can be measured in candelas. Conclusion. Understanding physical quantities and their units is fundamental to the study of physics and other sciences. It forms the basis for all experimental and theoretical work in the physical sciences. Proper measurement and unit usage allow for the accurate representation, comparison, and calculation of physical phenomena.